All right, so now we're going to talk about solving systems of nonlinear equations. Okay, so the goal is to solve systems of algebraic equations in the following form. Okay, so let's say f1, which depends on x1 to xm, all the way up to fm, which depends again on x1, all the way up to xm. Okay, so so if you recall, it's like when we first talked about root finding for a nonlinear equation, we introduced this idea of the Newton method. Okay, and in particular, it's like we derived the Newton method by considering a Taylor approximation of the function at the initial point. So we're going to try to do something analogous. So recall that the derivation of Newton's method for a scalar equation right, that we said that, well, you look at the function value at alpha, but expand it at around another point, and this is equal to 0, right? So this is f at this point I'm expanding about, plus alpha minus x times f prime at x, plus this Taylor remainder term, 1/2 f double prime at some unknown point c times alpha minus x squared. And then we assume that alpha is the root, so f at alpha is 0. And we assume that alpha minus x squared is small. If my initial point is close to the root. Okay, so this implies then that 0 f of alpha is approximately equal to f of x plus alpha minus x f prime of x, which means that alpha is equal to x minus f of x over f prime of x. All right, so so we construct a fixed point iteration, alpha n plus 1 is equal to alpha n minus f alpha n over f prime alpha n, right? So this is the Newton method. It's like, which is a fixed point iteration to some function f of x. Sorry, not f, let's call that g. Okay. Yep, anyhow. All right, so if you want to generalize this approach to systems of algebraic equations, right, then you basically have to generalize this Taylor expansion, okay, at least to leading order. So what does that involve? So that involves what is called the Jacobian, it's like of that system of equations, right? So the Jacobian is denoted J, right? It depends on this vector x. So J x1 to xm, which just involves essentially the partial derivatives of this, the various components of this nonlinear system of equations with respect to the degrees of freedom, which are x1 to xm, right? So I take the partial derivative of f1 with respect to x1, partial derivative of f1 with respect to x2, partial derivative of f1 with respect to xm. That's the first row, right? I keep doing. this now, but for the different components of this nonlinear function, vector valued nonlinear function. Okay, so this is what's called the Jacobian. And with that, I can generalize the Taylor expansion. Okay, as follows. So of the Taylor series. Right. So f at this vector alpha is equal to f at x plus the Jacobian at x times alpha minus x plus something which is big O of alpha minus x squared. Okay, all right, so let's just look at this to make sure everything is dimensionally consistent. This is an m by 1 matrix, vector, m by 1. This is an m by m, and this is an m by 1. Okay, so everything is an m by 1 after you multiplied it out. Okay, so you can follow essentially the same argument. If alpha is the root of this nonlinear system of equations, then this is the 0 vector. And we're going to assume this is small, so assume this is small. So I'm going to ignore it, right? So I get that 0, which is f alpha, is approximately equal to f x plus j x alpha minus x. So I get alpha is approximately equal to x minus j inverse times f of x. Okay, so Newton's method for systems is therefore nothing more than alpha n plus 1 is equal to alpha n minus j inverse alpha n times f evaluated at alpha n. Okay. All right. So, so that's the basic idea, right? Is that the main difference is that instead of the derivative of the scalar value function, it's like you have the Jacobian. Jacobian's a matrix. You have a matrix vector product here, okay, which involves the inverse. Okay, all right. So let me make a few remarks about this. So as is the case with the scalar Newton method, the convergence of Newton's method depends on your choice of initial conditions. And in addition, if you recall, it's like the rate of convergence depends on, in the scalar case, depends on the value, it's like of the derivative, it's like at the root. So something similar happens the convergence of Newton's method, the rate of convergence of Newton's method depends on properties of the Jacobian at the root. So you have quadratic convergence. If j at the root is invertible, right? And linear convergence if j at alpha is singular. So the third remark is that, well, if you look at the iteration, you have this j inverse term, so at each step you have to invert this j. So at each step you have to invert j alpha n. All right, and then the fourth question or remark is, what should you use as a stopping criterion? So what should we use as a stopping criterion? All right. So let me sort of try to answer a few of these things, or sort of address a few of these issues. Right, so in particular, let's look at this inversion issue. So if you inverting the Jacobian, right, so what you basically do is you write down a linear relationship, right? So you let yn be minus j inverse alpha n times f at alpha n. Right, so at each step we have to solve a linear system. Right, so j alpha n times yn is equal to minus f alpha n. And then once we solve this, right, we have that alpha n plus 1 is equal to alpha n plus yn. Okay. So the point is that, it's like in the lead up, it's like to this discussion about systems of nonlinear equations, it's like we talked a little bit about solving systems of linear equations, right? So as a subroutine, if you will, it's like in your Newton method, you have to implement one of these linear solves, and we've discussed various ways of doing this. You could do this with a direct method, say using LE decomposition, with forward or backward substitution, or it's like you can use some sort of iterative scheme. It's like to do this. In general, my suggestion is to probably just use an iterative scheme because it's part of an iteration anyway, right? So there's no real need, it's like to solve for the exact solution, especially if it's a large system. Okay. All right, so anyway, so that's sort of addressing this issue of inverting the Jacobian, and then the other issue, it's like I wanted to sort of briefly address is to discuss the issue of stopping criterion. Okay. So we had seen various types of stopping criterion before, right? There is an absolute error test, which is that say the norm of y is less than the tolerance. Okay, so that means the update is not really changing a lot. There's some sort of relative error test, which is maybe that the norm of y normalized to alpha n is not changing a lot, right? So maybe alpha n plus 1. Okay. And then there's also the residual error. Okay, which is that you look at f evaluated at alpha n plus 1. That is less than some tolerance. So those are some possible stopping criterion. And then you'll see that in all these things, there's some norm it's like which you're using. And of course, it's like you have choices as to what norm you use. Right? So there are various types of vector norms. So what vector norm to use? Okay. So let me just sort of briefly introduce a few of them, right? So we'll reintroduce a few of them. So the one norm, right, it's just the sum from k equals 1 to m of the absolute values of the components. The two norm is given by the sum of squares, but square root of that. So this is like the Euclidean norm, which you're familiar with. Right, and then the infinity norm, which we briefly discussed. It's like when we were talking about sort of systems of linear equations, the convergence of iterative methods. So that that's given by just the maximum value of the components. Okay, so the choice depends on the application. So which to choose depends on the application. And it might depend on, for example, what the significance of each of the components, it's like of the vector are, right? And to what extent you want to make sure that, say, all the equations, all the individual equations are satisfied as well as possible. So if you care about the, that every one of the equations, for example, has a small error, then you might want to choose something like the infinity norm. But if you only care that the solutions or the equations are satisfied in some sort of aggregate way, then maybe one of the p norms here, it's like would be more appropriate. Okay, in any case, it's like, all right. So let me sort of just briefly say what happens if you wanted to evoke these norms in MATLAB. Okay, so if in MATLAB, if you wanted to do one norm, you would just call norm y comma 1. You wanted to evaluate the two norm of a vector, you just call norm y comma 2. And if you want to evaluate the infinity norm, you just call norm y comma inf. Okay. All right. So so that's basically how you might set this up. Okay. All right. So let me just stop here for now, and we'll discuss the algorithm for this later.